Continuing our discussion on the monoclinic symmetry, we now have to examine two other symmetry elements which come due to the presence of translational periodicity. We have mentioned earlier somewhere in the passing that there is possibility of what is called a screw axis motion, which is denoted as T1, and then there are also what are known as glide planes. I think we gave some examples from Escher's diagrams and discussed the possibility of the nature of the glide plane and how it acts and so on. But now we will examine them thoroughly in terms of the monoclinic symmetry, and once we understand this in terms of the monoclinic symmetry, it can be extended to higher symmetry crystal systems and therefore higher symmetry space groups. So let us go to the next slide where I am describing the screw axis as simple as possible. Let us take for example the twofold symmetry, which we are all very familiar with now. So if this is the point x, y, z, it undergoes a 180-degree rotation. So suppose the twofold axis is along the unique axis being y or b, then we will have this as minus x y minus z. We pronounce it as x bar y z bar. So we have an x y z, we have an x bar y z bar related by these two operations, and then it comes back again. So it is a point group 2. We can invoke the presence of a point group 2 1 likewise, where we take this point x y z. Now instead of the twofold symmetry, it is a twofold screw operation. So what we mean by a twofold screw operation is that now we rotate this by 180 degrees and then not stop there, but translate it by half a unit along the y axis, which is the b direction. So if you have a, b, c as the unit cell dimensions and b is our unique axis, then the translation is along the b direction. And this will give us an equivalent point at half plus x bar y z bar. So this half adds on to y. So the equivalent points therefore will be x, y, z, and maybe I have to use the pen now just to indicate it. So I will use it x, y, z, x bar half plus y z bar. So this is x, y, z. So x, y, z now goes over to x bar half plus y z bar, and now if we operate the twofold rotation again on this x bar half plus y z bar object, that object now will go to another twofold rotation. So it will go that way, but it will now come to an equivalent point which is x 1 plus y z. So that means we have now introduced a 1 unit translation along the y direction. So in crystal structures or in general the monoclinic symmetry systems, it does not matter if we add a 1 translation, as we saw in the case where we want to generate equivalent points such that they come inside the unit cell, we do a 1 unit translation. So this 1 unit translation therefore gets tolerated, and so you have therefore equivalent points x, y, z, x bar half plus y z bar, which will define a new point group symmetry 2 1. And this point group symmetry 2 1 does not exist in general, it exists only if you have a crystalline system which is possessing a twofold axis. So translational periodicity will generate half translation component if you have this 2 1 axis. So when we say the 2 1 axis, what we do is we rotate by 180 degrees and the translation is 1 divided by 2. So it is a half translation. So the translation here is 1 divided by 2, half the unit cell about which the axis of rotation is located. It may be in the y direction, it may be in the z direction, it may be in the x direction. So suppose what happens here if it is in the x z direction. Suppose it is in the z direction, this diagram is given. So this is x y. So if z axis is the unique axis, what would be the angle between x and y? The angle between x and y will be what? So the angle between x and y, a and b, so the angle will be by convention gamma. So this angle therefore is the gamma angle, And so we have the two-fold rotation. The two-fold rotation can come back. So this is the representation of a non-unique axis operation of the two-fold in a monoclinic symmetry. Now what happens if the non-unique axis has a screw system? So it is now possesses a screw periodicity. Then we have a screw point group symmetry. Then we have this plus z, and the two-fold rotation takes it up there, and we add a half to the z value. So this is now this half plus z, and then we operate this again and add another half to z. It will come 1 plus z, but 1 plus z is same as plus z. So therefore we get two equivalent points corresponding to 2-1 screw operation, and therefore the number of objects that get generated either by the two-fold rotation or by the 2-1 screw axis will be 2. So the same object now generates the screw axis operation. So it is like, for example, driving a screw through a wall. So you have the screw and you want to put it through the wall. What you do is you rotate with a screwdriver. So it can be designed in such a way that one rotation of the screw will generate half unit translation in the given direction. So if you rotate the screw in the opposite direction, it will come out by half the unit. So you can do this operation back and forth, and therefore that is why this screw axis operation is a valid symmetry operation. And so we get the equivalent points x, y, z, x bar half plus y, z in the case of 2-1 axis, and this is how we describe the screw axis. And this is the only possible additional symmetry element which can come in monoclinic systems. So the monoclinic systems, as we saw before, has the two-fold, the 2 bar and the 2 by m symmetry, and therefore now 2 can have a 2-1 symmetry. So we will have therefore a screw axis which is replacing the two-fold here. That will give us the new point group, and the new point group can be present here as well. It could be 2-1 divided by m. That means a 2-1 operation with a mirror perpendicular to that. That is also a possible operation of the point group symmetry. So additional symmetry elements means additional space groups. The two Bravais lattices P and C will both see these additional space groups, and therefore we will have space groups like P21 and C21, P21 by m and C21 by m. But we will later on show that C21 by m is nothing but C2 by m. So that way we will have a control on the number of space groups which we can generate. In fact, I have listed it somewhere later on in one of the slides. So the screw axis operation, I think, is now understood fully. We will go to the next slide, which now brings in the issue associated with glide planes. This slide tells us a few more extra information than what we require, but this is all the information which we can give on a the glide operation. So here is, for example, an indication of a mirror symmetry. The mirror symmetry m we have already seen, that is the 2 bar operation, and it has no translation. For example, if you have an object here, this object will undergo a reflection across the mirror. The mirror is perpendicular, so you will get this operation taking the object onto the inverted image of the object. This is like you look through a mirror. When you look through a mirror, your face will appear, of course, right becomes left, left becomes right. So you know that is the enantiomorphous behavior of objects. So it is like taking the left hand and trying to fit the right hand. These two are enantiomorphous objects with respect to each other, because the left hand and the right hand combination will now give us an identity operation between this and that, which happens to be the enantiomorphous relationship. So similarly, the objects related by, so if this is x and if this is the reflection along the y direction, then you have x y bar z, which will generate that. Now what I have shown here is one unit translation. So this is your unit translation along the which axis? This is the reflection along the y, so it has to be either A or C. So either way, we have therefore the next object which will also appear to have the mirror symmetry. So the mirror symmetry operation is one unit translation also will appear. So this is how we will be generating the objects when mirror symmetry operates. So having made sure that this is clear enough for us, so we have x y z, x y bar z, x y z, x y bar z. Okay. Now we can have two types of possible operations, and I have shown you purposefully the operation of the B glide. The reason why I gave the B glide here is for a reason. The B glide can, the mirror has to be perpendicular to the axis of symmetry. The axis of symmetry, let us say, is y, that is the B axis. If the B axis is the axis of rotation, then the perpendicular direction to B will have either A or C. On the other hand, if I show the B glide, what it essentially means is that it has to be, the unique axis has to be either along A or along C. So, this therefore is the non-unique axis representation. I purposely show this because you might come across situations where you have to deal with non-unique axis information. So, when such an information is required, therefore, it is better to know about the B glide. It does not matter whether it is a glide or a B glide or a C glide, it is along the axis. The only thing which we have to remember is that the mirror reflection occurs perpendicular to the axis of rotation. So, the axis of rotation either is with A or with B or with C. When we talk about monoclinic systems, the axis of rotation is always B unless otherwise specified, because we take unique axis as the B axis. So, here what you see is therefore x, y, z. Now, it undergoes a mirror reflection, and after the mirror it translates by half the unit, in this case along the B direction. So, this is B divided by 2 representing the B glide. Okay. So, the B glide is therefore can be perpendicular to either to A or to C. So, the translation now is associated with half the distance of B. Now, we operate this glide, again a mirror symmetry, and add half to that. So, the half is in the direction along the line parallel to the mirror. So, the half translation we add is in the line parallel to the mirror. So, your axis of rotation is perpendicular to the plane, and that is why we say it is gliding down that particular direction, and that is why this operation is referred to as the glide operation. If you go back to the very first class or the second class, you will see that we did discuss about this in terms of a Escher diagram, and you can go back and check that Escher's diagram again and see how this operation is coming up, the glide operation. There it is very clearly indicated with respect to an object. So, systems which will have the glide plane operation will also now fall into the definition of our required space group information, because of the fact that we can now have one translation unit, and that translation is in the periodicity repetition of the object in the crystal. And therefore, since it is a crystal, we can have this kind of operations. We can also have the operation because we now refer to a plane, and the axis is now perpendicular to a plane. Like in this particular case, the axis is coming towards you and the mirror operation is perpendicular to that. So, when we take such a situation, then the possibility is that it can also go along the diagonal direction. So, there are three types of diagonal glides that are possible: A plus B by 2, B plus C by 2, A plus C by 2. Now, my suggestion is that you draw similar diagrams as I have drawn on the right side to see an n glide. Even though I have given an n glide, I would like you to mark the axes about which the n glide operation takes place. Suppose I show an n glide like this, where we have the operation taking it half plus. Now, this half plus means that we not only have the half translation in this direction, we also have a translation in the direction perpendicular to that, but in the plane, associated with the plane. You see, this is the plane. Okay. So, we have the translation, we go half the translation in along the plane direction, perpendicular to the plane we go. So, effectively we are going along the diagonal. So, you have this translation half unit, and then we go half above, which is now parallel to this plane. So, the plane is like this. So, we have two translations, one down here and another going up there. So, effectively you have this half plus also coming in here. This half plus tells us that it is an n glide, and the notation for the n glide is line and a dot, that we know already from our early classes. So, therefore, we have again a translational periodicity restored by this operation. So, for the glide planes, therefore, we can have either an A glide or a B glide or a C glide, depending upon the unique axis definition in monoclinic. But if we go to orthorhombic and higher systems, we do have this all possibilities of A, B and C. The only thing we should remember is the B glide cannot be perpendicular to the B axis, okay, and A glide cannot be perpendicular to A axis, C glide cannot be perpendicular to the C axis. There is a special case of A plus C by 2 which is indicated with a star here, that will occur only in cubic systems, because in a cubic system, and probably it can occur in rhombohedral systems as well. In rhombohedral and cubic systems, the direction of the axis is not along either x or y or z, and as a result we can have this kind of glide planes which are very unique. They do exist and they create some different kinds of space groups, but we are not going to deal with them because they become reasonably complicated for this course. But we should know that such a thing also exists. The glides can be along all three directions, because your definition of the glide plane is only with respect to half translations, and your A, B and C are not necessarily the axis in case of rhombohedral and the cubic systems. There is another thing called the diamond glide, which will occur in tetragonal systems, and this could be again having a 1/4 of translation, and this will combine both A and B directions. Again, we were not going to discuss this because this probably generates only 1 or 2 additional space groups in the among the 230. So we are not, as I mentioned already, not going to study all the 230 space groups. That is not our intention, but we should see how the space group develops making use of these combinations, which we are now trying to attempt. For example, we have already seen the types of space groups which can occur from non-translational point group symmetries associated with monoclinic. Watch my words, non-translational point groups. That means there are no translational symmetry associated with those point groups. So we got these P2 PM, P2 by M, C2 CM, C2 by M, 6 of them. Now we are associating the 2-1 screw axis and also the A glide, C glide and N glide, and therefore we will get additional space groups. We will see how many additional space groups we get and what kind of properties they will have. We will then formally study space groups in later classes. That is not the, it's not going to be the end of the show here. We will just see how many space groups are coming, but how the space groups really relate and get to the equivalent points, and then make sure that these equivalent points which we have generated form a realistic definition of a space group, that we will see in the later classes. But at this particular juncture, we just see how many space groups are possible with the addition of the translation involved symmetry point groups, which are involving 2-1 screw A, C and M, and that will tell us something else. Now this is a slide taken from a book, so it looks ugly, but I think you can live with it because we just took a scanned copy of it. So here you will see all issues associated with monoclinic systems. So we have taken only the monoclinic systems and their corresponding equivalent points. Of course, diagonal glides are also given here, for that applies only for the tetragonal system. So we will not worry so much about the D glide, but all other glides will apply to monoclinic as well as orthorhombic systems. Right now we will discuss it with respect to monoclinic, because we have understood only up to monoclinic. We have not discussed the orthorhombic as yet, but these are the equivalent points which will come to your rescue and tell you how the group symmetry has developed. For example, if you take an axis 2 which is parallel to A, by parallel to A I mean along the A direction or along the x axis. So if there is a twofold along the x axis, what happens? The x axis value will not change. So you will have x, y, z, x, y bar, z bar. So the y and z will change. Similarly, if it is along the B direction, then we know that it will not change along the y axis. The y value will not change. Similarly, the z value will not change for the C direction. So having noticed that, see for example with these equivalent points which are operating on the twofold, the 2-1 axis can be perpendicular, it can be along A, can be along B and also can be along C. So if the 2-1 axis is along A, we have x, y, z, and wherever the 2-1 screw operates, that would be the direction where we have to add a half. So for example, if we have x, y, z, we add a half to x if it is along the A direction, half we add along the y if it is along the B direction. So for a unique axis monoclinic system, the equivalent points will be x, y, z, x bar, y plus half, z bar. So, as a consequence, we now see the possibility of existence of 2 1 axis in all 3 directions. At this moment, since we are discussing only monoclinic symmetry, it will be either along A or B or C. If it is along B, that is the convention which we use for monoclinic systems. Likewise, now we go over to the plane. In case there is a mirror plane perpendicular to A. So, when we describe the mirror plane, it is either perpendicular or normal. In fact, this table is a little funny, because if we say parallel here, we can say perpendicular, but if we say along there, then we can say the plane is normal to the A, B or C. Okay. So, we can say twofold is along A, B or C, and the plane mirror plane is normal to A, B or C, or we can say twofold parallel to A as is written here, and perpendicular to A as is written here. This is just the way in which you can talk about the existence of twofold and mirror. Different textbooks give different notations, so I am telling you both. So, many of the textbooks say the mirror plane is normal to A. Then you will start wondering, what is this normal to A? It is nothing but perpendicular to A. Okay. So, what happens is only the value of the coordinate associated with this axis A, B or C will change. So, x y z will go to x bar y z, x y z will go to x y bar z, and x y z will go to x y z bar. If it is an A glide, the A glide, as I mentioned, cannot be perpendicular to A, it can only be perpendicular to either B or C. So, depending upon to which direction it is perpendicular, that perpendicular direction will change sign, and the addition will be always with respect to the A glide. What I mean to say here is, if you take x y z, you see that you have an A glide perpendicular to the B axis, then your A value will be x plus half, the equivalent point, and then y will change to y and z will remain the same. If it is along the C direction, z will change the sign, but the addition is always with respect to the axis about which the glide plane occurs. Similarly, the B glide and the C glide are illustrated here. You notice for the N glide perpendicular to A, there will be additions both along y as well as the z directions, because now the N glide can be since it is perpendicular to A, the translations will be in directions perpendicular to the axis of that axis. So, since N glide is perpendicular to A, the translation components can be along both B as well as C. So, B and C will get the additions of y plus half and z plus half. So, that is how you can evaluate the nature of the glides as well as the nature of the 2 1 screw axis. Diamond glide is a little more complicated. I will not go and describe this now, and I do not think we need to worry about it at this moment at the level of the course which we are offering now. These will of course generate additional space groups in very few crystal systems, cubic probably and tetragonal to some extent. Other crystal systems will not have the diamond glides. So, as a result, very few space groups. If you come across any of those space groups, you can specially analyze them and see whether you can get information on this. So, what happens with the presence of the 2 1 screw and with the presence of the glide plane? You get additional space groups. Now, the additional space groups you will get from the P21 or with the 2 1 screw axis or P21. You can also get C21. We will later on show it is nothing but C2. There is nothing called C21. We will show that in terms of derivation of the equivalent points, which is the next, probably in the next class. And then we have the space group P21 by M, and since 2 1 cannot exist with the C glide, we will have C2 by M. So, these are the additional space groups over and above the 6 space groups we saw which have no translational component. Here the space groups have translational components. The additional space groups coming from glides plus combining with screw axis are given here. I want you to think for a moment and see whether something is missing here. I say that something is missing here. We have missed a few space groups, and those space groups involve what? They involve the diagonal glides. So, I am going to write them So I am trying to see whether I can write them. I will get the pen across here and write them down here. So it will be now Pn and P2 by n and P21 by n. These are additional space groups. So we can have the combination of the screw axis as well as the glide planes, as you can see here, and along with that we have the P2 by m and the Pn. Pn will be similar to Pc, except that now the translations are along two different directions, x as well as z, assuming y axis is the unique one. Then we have the, in addition to that, can you have Cn? Can you have C2 by m? Can you have C2 by c? We have to add those. We have already added C2 by c here. Can you have C2 by n? These are things which you have to explore yourself at home, and you will see that those possibilities are already incorporated into the space groups here, except that it depends upon how you do the additions. See, as we saw here that C21 can be shown equal to C2, the operations with the n glide with the C centering is an issue which we can reduce it to a translation along the C direction by doing some changes in the A, B, C directions. That is a complicated issue. Either we will do it later as an assignment part, or we will see how we can show. In fact, we can also do this as an assignment part later during the coursework. So C2 by m equals C2 and C2 by m equals these two issues we can take care as we go along. So we see that we have the 2-1 screw axis shown here. Now the glides and the screw axis can occur in other crystal systems also. We have so far considered the monoclinic system only. Of course, triclinic cannot have any of these systems, but once we have the monoclinic system which is associated with a two-fold axis or a mirror perpendicular to the two-fold axis, we can have these additional translational components associated either with the either with the two-fold operation or with the mirror operation, and therefore we will have these. So obviously the other space groups like or other crystal systems, orthorhombic and higher symmetry, the moment we talk about higher symmetry, we will have higher symmetry information in them. So we can have the 3-fold rotation, we can have 4-fold rotation, we can have 6-fold rotation. Then obviously we will have translational components associated with them, and those translational components associated with them will give us the information about the possibility of having 3-1 and 3-2. Now you notice that the 3-fold axis can be 1/3 rotation as well as 2/3 rotation, 1/3 addition as well as 2/3 rotation. So 1/3 is when we draw the screw. Now the screw is, let us say, 3-fold geometry. Then we can have one turn which gives you 1/3. Second turn will give you 2/3. The third turn will give you the full turn. Similarly, the 4-1, 4-2, 4-3. And 6-1, 6-2, 6-3, 6-4, 6-5. So all these possible rotations are or can be located, and therefore we have shown that on the right side. I have shown it on the right side where you see the type of operations. We have discussed it already once. So these will now give us the 3-1, 3-2, 4-1, 4-2, 4-3, the equivalent points which get generated by these operations are also indicated here. So effectively we have covered the possibility of glides and screw axis, and we will have them in trigonal, tetragonal, hexagonal systems. And can we have it in the cubic system? I have asked this question to you so that you can think about how to do this cubic operation and how the cubic system can have these kind of operations. Like you can think of a situation where you have a 3-fold axis in a cube. So obviously the possibility of 3-1 and 3-2 in a cube is indicated. You also have the 4-fold rotation in a cube. So those are also indicated. But the fact that it is a cube has certain properties. So, which property of the crystal system dominates and which does not dominate is very important. So, that is how, for example, when we talked about this C21 and C2, it is the C operation which dominates. So, once we have a C centered lattice, we will take that C centered lattice as the main concern for generating equivalent points. So, you will have x, y, z, half plus x, half plus y, z. Any other component which will involve translations in either of these two x or y is secondary. So, therefore, the secondary interaction can be ignored because it is already built in to the primary interaction. So, when we say a space group is let us say CC, the operation of this capital C is more crucial than the operation of the small c. That is how, for example, we will not have a glide associated with C centering, and that is where we see that the importance of the dominance of the lattice type comes first. This is something I thought you should notice before we go further.